In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe. Are we alone? Or is there another Earth-like planet somewhere in the universe?
We have a fantastic goal yet for the next generation, which is to find planets that remind us of home.
I believe we're right on the brink of having the technological capability to actually answer a question that humanity has been asking itself for the last 2,000 years.
Another Earth could be as close as our nearest star system.
We're right on the threshold of being able to find these planets.
There could be twisted Earths under bizarre suns. Can we find these other Earths as they float hidden in the billions of stars and trillions of planets of the universe? Is there another Earth in the universe? It's perhaps one of the oldest ideas since mankind was able to look up at the stars and wonder.
Back when people were sitting around their campfires and looking up at the stars and imagining them as other campfires with other tribes around them.
What exactly do we mean by another Earth? It should support Earth-like life.
When you boil it down, life needs three very basic things to exist. It needs a liquid medium of some sort to do its chemical reactions in. And we think water is the most likely liquid medium. It's very prevalent in the universe. We also need to look for the basic building blocks of life, the molecules that can help to put life together, the phosphorus in your DNA. And we need to have an energy source. It turns out that a terrestrial planet that has water on it pretty much has all of those things we need.
Not all planets capable of supporting Earth-like life would have to be carbon copies of our own Earth.
So you can think of it like a series of different types of houses. If you go into a city, for example, there will be grand mansions, and there'll be smaller, more modest little two-bedroom homes, and there'll be city studios and skyscrapers and so on and so forth. All of these house people, all of these can help house life. And so we think about that when we go out into the universe looking. We're going to be looking for houses of all different kinds and keeping our minds open as to what could support life.
Astronomers have found over 300 exoplanets, that is, planets outside our solar system. The vast majority are gas giants, which are easier to find than small terrestrial planets like our Earth.
To build instruments to analyze those Earth-like planets, we have to anticipate ahead of time what the chemicals might be in that Earth-like atmosphere. For that reason, we need theory, we need models.
Victoria Meadows is in the planet modeling business. She heads up the Virtual Planet Laboratory at Seattle's University of Washington. The group, spread across institutions around the country, builds worlds that may exist in the yet unexplored universe.
The Virtual Planetary Laboratory allows us to simulate what planets might look like from space and what their environments might be like in advance of actually discovering these things out there in the universe. So it allows us to explore what planets might be like.
In the Virtual Planet Lab, fantastic worlds can be built, like a science fiction novelist with a supercomputer as a writing partner.
So we can take something that's like the Earth, but we whip away the sun, and we replace it with a star of different size and temperature. So what we've done with the Virtual Planetary Laboratory is modeled planets that started out as Earth-like and put them around stars that were much hotter, with much stronger UV radiation, for example, than our own sun.
The models can produce bizarre alternate Earths, filled with plants that are bright red, orange, or even pitch black.
Photosynthesis can vary greatly depending on the light of the star that's shining on it.
Planets around F stars, for example, where the light from the star is much bluer, the plants there will tend to absorb more blue light, and so those plants could potentially be more likely to reflect red, orange, and yellow light, and so will appear red, orange, and yellow to us.
Plants on a world around weaker stars could evolve their coloration to use every bit of energy falling on them.
If you go down to much cooler stars than our sun, to M stars, plants on planets around M stars might in fact be black because they want to absorb as much light as possible to do their photosynthesis and to feed.
And then there's the water world planet, a theoretical Earth circling a volatile M-type star that constantly hits the planet with outbursts of deadly radiation.
And how does life cope on the surface of that planet? Is it possible to have life even when you have a flaring M star? It turns out that you can actually live about 9 meters underwater on a planet around an M star and still escape the worst of the flares, but still have enough light to be able to do photosynthesis and to survive.
Everything looks good from here.
And as future exploration missions are being drawn up, many scientists are focusing on what it would take to detect the byproducts of life on a distant planet.
Life produces gases. Life stinks. You can smell it. And we're going to look for those gases with these high-resolution spectrometers.
So what we really need to do is take the light from another Earth-like planet and analyze it to find out what the chemical composition of that atmosphere is.
Finding the locations of planets is something that UC Berkeley astronomer Jeff Marcy is very good at. He and his astronomy colleague, Paul Butler, are credited with finding more exoplanets than anyone else.
A planet that's farther from its host star will be very cool. And so there's a domain in between that we sometimes call the Goldilocks zone or the habitable zone, where the temperature is just right. And by just right, I mean lukewarm so that water would be in liquid form. And of course, it's liquid water that's the prerequisite for life.
When we look at other planets and we ask, could there be life on other planets? My first question is, could that planet support liquid water? Yes, I'm interested. No, I'm not interested. It all comes down to show me the water.
Water is an amazing substance. We are frankly fortunate that the universe has something called water. It's the great cosmic cocktail mixer. Water is the critical stuff that allows the chemical reactions to take place that eventually lead to life.
But this special zone, where liquid water can exist, varies from place to place. If a star is a hot O type, the zone will be farther out from a sun. If it's a cool M type, the zone will be closer in. And it even changes with time. Stars are not stable. Even our own comfy habitable zone here on Earth will change in a few million years when our sun grows older and much hotter. Current technology doesn't exist to take pictures of distant exoplanets. So astronomers use the solar system star as a sort of proxy for a planet, since both were formed from the same planetary disk of material.
How do we know what a star is made out of? We don't go there and sample it. Your experiment would melt.
Astronomer Wes Traub heads up the effort by NASA's Jet Propulsion Laboratory to come up with the next generation of instruments that will look at planets outside our solar system.
What we do is we just simply look at it and we break the light up into different colors. This was done several hundred years ago by Newton. He discovered that if you put a prism in a ray of sunlight, it breaks it up into blue, green, red. And you look at these different colors and you discover something very startling all of a sudden. There are parts where colors are missing. And these missing colors are a fingerprint of the constituent of the sun that you're looking at.
With current technology, we can't directly view a spectrum of a planet outside our solar system. But eventually, more powerful instruments will allow us to use the same technique to fingerprint a planet for evidence of life.
If we look at that light from the planet and break it up with a prism or something similar, we can tell what the planet is made out of, and that's how we know whether our planet has oxygen, like our atmosphere, whether it has water vapor in the atmosphere, whether it has ozone, carbon dioxide, and nitrous oxide.
But nothing in the universe stays the same over time.
When our Earth formed 4.5 billion years ago, it had a very different atmosphere than it has now.
It's a challenge that Meadows and her team anticipate as they build their models of other Earth-like planets.
We would be very short-sighted to look just for an oxygen-rich planet at the same stage of development. So the thing is, when we go out to look for habitable worlds, they could all be extremely different. They could be very diverse.
And if we find another Earth, what are the chances we'll find a civilization on it that we can communicate with? What's the number of intelligent civilizations that might exist on other Earths in the universe? What would have to go into such a calculation?
How many stars are there? How many of those stars have planets? How many of those planets are close enough to have water? And on and on.
That's a problem that astronomers Carl Sagan and Frank Drake took on decades ago. Drake came up with an equation that estimated that up to 1 million civilizations may exist in just our Milky Way alone.
The Drake equation is this series of numbers that are trying to be put together in such a way to give us a kind of way of even closely estimating how many other intelligent civilizations are out there.
Peter Ward, a professor of biology and geology at Seattle's University of Washington, thinks the Drake equation greatly overestimates the number of advanced civilizations that could exist on other Earths in the universe. Ward and astronomy professor Don Brownlee's book, Rare Earth, explains why they think complex life, animal life like humans, may be rare in the universe.
We began to think that it was just too simplistic, that there's other stuff involved.
Ward cites a number of factors that he thinks would lower the original Drake estimates of how much complex life could exist in the Milky Way, and by extension, the universe.
First of all, plate tectonics. Plate tectonics is continental drift, and one wonders why would that have anything to do with the frequency of life on the planet? Plate tectonics also produces a recycling of elements, and that recycling does some very fundamental things. The most fundamental thing it does, it produces a temperature gauge. It's like a thermostat on the planet. If we get too warm, plate tectonic processes help us cool off.
Then there's the presence of metal on the planet.
Secondly, if you want to be an intelligent civilization, you better have metal. Metal's hard to find on a planet like Mars or Venus. But plate tectonics rotates everything, causes cracks, up come the heavy metals. What else do we need? We need a good Jupiter.
Having a gas giant like Jupiter, with its strong gravitational pull in the outer reaches of a solar system, protects the inner planets, those potential Earths, from frequent catastrophic impacts.
And the reason is those Jupiters sweep up gravitationally the asteroids and the comets, flinging them away, allowing the Earth to survive without so many impacts by that debris. And so it's those protective Jupiters that allow life to proceed without impacts by these asteroids and comets that would cause mass extinctions, as indeed happened to the dinosaurs.
65 million years ago, an asteroid hit Earth and wiped out most of the dinosaurs on the planet.
Those dinosaurs went out because Jupiter failed on the job and should have been fired. Bad Jupiter that day. It let one of these asteroids sweep by, but we've seen what it usually does. Comet Shoemaker-Levy that smashed into Jupiter at the last part of the last century. That's what Jupiter generally does. So good Jupiters are good things to have, and you can make equations for this.
When considering the habitability of planets, most astronomers place great emphasis on finding worlds in the habitable zone around a star. But Ward and his co-author believe that a planet's position within the larger galaxy is also critical.
So that's why we have defined, or did define, something we call the galactic habitable zone. That area within a galaxy, not too close, not too far. It's a Goldilocks area within our galaxy that's just right.
They came up with 9 factors that make up a so-called galactic habitable zone. Earth's position in the galaxy is considered. Away from killer neutron stars, black holes, and deadly gamma ray bursts. They included the percentage of stars that have planets and the percentage that have microbial life. They even estimated how often planets might have all their life extinguished. Earth itself may have narrowly missed such an event in 1998. Then, a high-density star called a magnetar burped out a flare of deadly gamma rays, unleashing as much energy in 0.2 of a second as the sun will put out in the next 100,000 years. Luckily, the magnetar was located 20,000 light-years away from Earth.
A really good question would be to ask, what would have happened had that magnetar that burped not been 20,000 light-years away, but 10,000 light-years away? Could there be a case where we had something within a few hundred light-years? If that were the case, new calculations suggest it could punch our atmosphere off, woof, in one burst. And you go, I can't breathe. Now that's catastrophic, and that is totally possible.
Humans may be just a cosmic fluke in the universe. The optimistic assumptions of the Drake equation may just not hold up with what astronomers have learned in the past decades.
The Drake equation was a fantastic construct, but it was done in the 1960s. We know so much more now. So we've added in stuff that wasn't known then. And I think it makes it more accurate, but ultimately it also brings down the numbers. And the million civilizations I do not think can be supported by current understanding.
So how many other Earths supporting advanced civilizations does he think may exist in our Milky Way?
I've been asked over and over to make a prediction, and I'd say, well, we know it's at least one. It's more than one, I think. But I think it's more than one, but way less than 1 million.
Locating another civilization may happen as astronomers concentrate on looking for other Earth-like planets. But finding those Earths in the first place is a huge technical challenge for scientists. Unlike the stars that have been cataloged, planets can't be seen using current technology. A planet, when examined from light years away, is almost on top of its sun as viewed from outside our solar system. And to make matters worse, an Earth-like planet, even one many times larger than our Earth, reflects only an infinitesimal amount of light compared to its star.
So here we have a bright star and a planet which is 10 billion times fainter. It's hard to imagine what 10 billion times really is, but the way many of us think of this is, suppose you have a firefly, a very small firefly, a very weak light, and suppose that firefly is orbiting around or flying around a lighthouse. And suppose you're trying to look at this firefly flying around this lighthouse from 3,000 miles away. That's something what it's like.
Let's assume you could find that speck of a firefly from across the country, and then you had to figure out what that firefly is breathing by analyzing the gas it's exhaling. That's the challenge that faces an astronomer who first has to find a planet, then figure out how Earth-like its atmosphere is. But astronomers have figured out indirect ways to find extrasolar planets.
If that were the star and very bright, and this were the planet, and it moved in front of that star, the star would get dimmer, and you would notice that.
It's called the transit method of discovering a planet, since it depends on seeing the travel or transit of a planet across a distant star.
The amount of light it blocks when it's in front tells us how big the planet is. So we use that to understand whether it's a small planet like Mercury, a planet like the Earth, or a huge giant like that of Jupiter. And we use the orbital period and the temperature of the star to tell us if it's in the habitable zone.
The orbital period is how long a planet takes to go around its star.
Then we'd go on its way and come back again a year later and do it over again.
When that period is combined with the type and size of the star, the information will tell scientists if the planets that are found are potentially in a habitable zone. The transit method works if the observer or the telescope is in the same plane as the star and its planets. But if you're above or below the system, another technique called the radial velocity method might be used. That method depends on careful observations of a distant star to watch if it's being gravitationally tugged back and forth by an unseen exoplanet. Astronomers can use that information to figure out details about the exoplanet that's influencing the star. Equipped with these tools, astronomers are finding hundreds of planets. Some never dreamed of in astronomy textbooks. Super Earths, hot Jupiters, and even some close cousins to our own Earth. In the search for other Earths in the billions of stars in the universe, astronomers have found a relationship between the composition of a star and the probability that it may have planets, both Earth-like and otherwise.
The stars that have heavier elements in them, the iron and the nickel and the silicon, have heavier elements for a good reason. Those stars formed out of molecular clouds in the Milky Way galaxy that collapsed down to form the star, and in so doing, left some placental material around them that eventually coagulated into the planets. So it makes sense that stars that formed with lots of heavy elements will form planets that also have lots of heavier elements.
Astronomers call the proportion of heavy elements in a star its metallicity. But that doesn't necessarily mean it has a lot of metal in the conventional sense.
Metal, for an astronomer, is any element that's heavier than hydrogen or helium. So in astronomer speak, lithium is a metal, sulfur is a metal, chlorine is a metal, and not just elements like iron, gold, and silver.
An Earth-like exoplanet not only needs heavy elements in its composition and to be in a star's habitable zone, it also needs to be the right size to sustain life. Right size means it can hold on to its atmosphere and have plate tectonics and volcanoes, both considered critical to regulating a planet's temperature. To do all this, astronomers estimate that the smallest a planet can be is 1/3 of Earth's mass. On the high side, a habitable planet cannot be greater than 10 times our Earth's mass. The very existence of exoplanets has gone from theory to reality only in the last decade.
A little over 10 years ago, we had no known extrasolar planets at all. The only planets we knew of were those orbiting our sun. And now we know of planets orbiting other stars. And of course, what's really exciting about these planets is that some of them may be habitable, and so there's a chance that there's life on some of them.
Of the hundreds of exoplanets found, some may not follow the familiar blueprint of planets in our solar system.
We found these bizarre Jupiters that orbit very close to their star. They're blowtorched hot, and these Jupiters undoubtedly got close to their star by migrating inward.
Sometimes the formation of a Jupiter-mass planet can be kind of a death knell for terrestrial planets in the system.
And what if we had been unlucky enough to have such a Jupiter in our solar system?
It would have slingshot the Earth right out of its orbit into the vast, cold darkness of outer space, and the Earth would eventually die off as a cold, dark hulk.
Over 300 exoplanets have been discovered, and more are being found all the time. But the majority are monstrously huge gas giants that hold little promise of being truly Earth-like. In the Pegasus constellation, some 50 light-years from Earth, the planet 51 Pegasi b can be found. It was the first planet discovered outside our solar system. A gas giant as big as Jupiter, but orbiting much closer to its star. It races around its sun in just 4 days. The planet 70 Virginis b is even farther away than Pegasi, at 60 light-years. It's 7.5 times as massive as our Jupiter. At first, it was believed to be in the habitable zone of the star, so it was nicknamed Goldilocks. Later calculations showed that it had an eccentric orbit that brought it to within 27 million miles of its sun, which is roasting hot, so it's no longer considered to be in a habitable range. The massive gas giant Trace 4 is over 1.5 times the diameter of our Jupiter, making it the largest planet found so far. It's 1,400 light-years from Earth. This gas giant, even though it's much larger than Jupiter, only has a little over 3/4 of its mass. It's a hot Jupiter, zooming around its sun in only 3.5 days. Astronomers haven't been able to find true Earth-like planets outside our solar system because they've not yet been able to detect such relatively small rocky planets as our Earth. The technology is just not there yet. But astronomers are having more luck finding what are termed super-Earths.
People actually being able to discover planets that could potentially be in the habitable zone around other stars. And one classic example of this is a planet called Gliese 581c.
The Gliese 581 system is located about 20.5 light-years from Earth in the Libra constellation. Gliese 581c has 5 times the mass of our Earth. There were hopes that 581c would be the first Earth-like planet found in the habitable zone of a star, but that turned out to be wrong.
Probably it's a little bit on the wrong side of the fence. So that one, instead of being a super-Earth, is probably a super-Venus.
It's like our own Venus, way on the hot side, with possible 600-degree temperatures, but also more massive than Venus. But Gliese 581c has a relative a little farther out and cooler. It's named Gliese 581d.
And this one is at the far back end of the habitable zone, where it's quite cold. When you initially look at it, you think, well, maybe that's a bit too cold. But it turns out that if the planet potentially has enough greenhouse gases, it might be possible to make that planet warm.
Another promising Earth-like planet may be HD 69830d. This is a big planet, 17 times the size of our Earth. It's about 42 light-years away from our solar system in the constellation Puppis.
HD 69830d is a potential planet where life could form because it has approximately the right temperature.
The planet could have a temperature between that of Venus and Earth, and it has a close to circular orbit, meaning it won't get toasted by close encounters with the star it's orbiting.
So you can have liquid water. The mass of the planet is maybe not so good. It's about 17 times the mass of the Earth, which could be a solid ball of rock, or it could also be a gas ball like Neptune in our solar system.
When NASA's able to fly future planet-finding missions, it's expected that astronomers will be able to get a spectrum that will give us much more information about the composition of the planet. They may be able to figure out if the planet has a solid surface, or that it's a water world, or perhaps something else entirely. The search for other Earths has taken astronomers light years from our neighborhood in space. But could another Earth exist in our own solar system? While astronomers look at star systems many light years away in hopes of finding another blue marble of a planet, other Earths may be a lot closer than that.
So imagine going back 3.5 billion years ago and visiting our solar system. You'd have seen 2 blue marbles here. Earth, water, thick carbon dioxide atmosphere, warm conditions, life. Now imagine moving a little over, you see Mars. Water on the surface, thick carbon dioxide atmosphere, warm conditions, possibly life. Well, the 2 planets start evolving. Earth stays habitable. Mars doesn't.
Both Venus and Mars are just on the edge of the Goldilocks zone of habitability. Both may be cases of failed Earths. Once you fall off that path, you may never be able to come back.
Mars is a lesson for what you need to maintain habitability for a long time. And the answer, we think, turns out to be big. You have to be as big as the Earth to maintain habitability for a long time. Mars is too small. Being too small, it has no way to recycle its elements and has no way to hold on to its atmosphere for a long time. So size matters.
And while Mars is now too cold, Venus, our other would-be Earth, has the opposite problem. It's too hot.
It was a little bit too close to its star, too close to the sun. It got hot and it stayed hot. And so all the carbon dioxide, the CO2 and so on, that formed on Earth, formed also on Venus. But on Earth, it was incorporated into rocks. On Venus, it stayed in the atmosphere. And the atmosphere basically is global warming to the nth degree. Sunlight comes in and it just doesn't leave. That planet is like the inside of a pizza oven.
Venus failed because it was born in the wrong place. Mars failed because it was born the wrong size. So we have an interesting story here, Venus, Earth, and Mars. Venus is in the wrong place. Mars is the wrong size. Earth is the right place and the right size.
So if the planets in our solar system aren't great candidates for being Earth-like, our closest galactic neighbor, Alpha Centauri, may harbor an Earth-like planet. At a little over 4 light years away, in galactic terms, it's next door.
I think that there's a good chance that Earth-like planets are orbiting around either one or both stars in the Alpha Centauri system.
Astronomer Greg Laughlin has done computer modeling to show that Earth-like planets should exist in the system.
There's a number of reasons why Alpha Centauri is the best star in the sky for hunting for Earths. Alpha Centauri is very close by. Alpha Centauri has 2 sun-like stars. Alpha Centauri has a large quantity of the kinds of heavy elements that go into building planets.
How close is the Alpha Centauri system to us? First, imagine shrinking our sun down to the size of a grain of sand.
A grain of sand is just about the smallest object that you can see with your eyes, and just about the smallest object that you can actually feel with your fingers. And at the scale where the sun is the size of a grain of sand, the Alpha Centauri system is 3 more sand grains placed about 5 miles away. Now, if we wanted to get a similarly good system to Alpha Centauri, we'd have to actually go all the way over the horizon to find another stellar system that's good.
And it turns out that the stars of the Alpha Centauri system should have plenty of raw materials to make planets out of.
Alpha Centauri has a higher metallicity than our own sun does, and that implies that planet formation was a process that took place relatively easily in that system.
And last but not least, Alpha Centauri's 2 main stars provide an additional benefit.
The initial indications show that there are no Jupiter-mass planets in the Alpha Centauri system. That makes it more straightforward for terrestrial planets to form around either or both of the stars.
That's because large gas giants form around cores of ice that are as big as our entire Earth. So these giants need a lot of cold space to form these cores. Think of how far out Jupiter is from our sun. However, when you have 2 stars with overlapping orbits in a system like Alpha Centauri, there isn't a space in the system that's big enough and cold enough to allow the formation of these gas giants.
So we expect that the planets that exist in the Alpha Centauri system, if they're there, they're terrestrial planets like the Earth or Mars or Venus. They're not gas giant planets like Jupiter or Saturn.
What if we could actually survey how many Earths are in our part of the universe? What if we could peer directly into the atmosphere of another Earth that was light years away? In order to find another Earth, astronomers have to eventually overcome the huge technical challenges of how to view a distant planet. It's a problem that NASA has tackled much like the race for the moon, with plans that stretch out over decades. The first exoplanet-finding mission will be Kepler, which launches in 2009. The NASA survey project is named after the 17th century astronomer Johannes Kepler, who discovered the laws of planetary motion.
What Kepler will do is so utterly simple and yet extraordinarily powerful, it brings tears to my eyes. What Kepler will do is simply be a space-borne telescope and stare at the constellations Cygnus and Lyra, taking picture after picture after picture, with the goal of looking for stars that dim when an Earth-like planet blocks some of the starlight. And it will be the first time that we humans detect other Earth-like planets around other stars.
The principal investigator for Kepler is William Barucki. He's been championing the mission for 25 years.
Kepler basically is a space mission that puts up a very large telescope. It's very much like a camcorder. It's always taking pictures of these stars, sending that information back to you.
The mission is a comparatively small survey project to look at a fixed portion of the sky for an initial time of 3.5 years.
The main result from Kepler will be to give us a statistical count. It's a head count of what the population is. You know, how many small planets do you have and how many large planets do you have?
Kepler's results will in turn be used to help decide what will be built for the next generation of planet-finding missions.
Kepler really is one step along the way. It's to try to find Earths and find out whether they're frequent. If they are frequent, they must be close, so we can build a modest instrument. If we don't find many Earths, What that means is before you're going to find another one, you're going to have to look at a huge distance into space. So you're going to have to build a much bigger, much more expensive instrument.
The most majestic, spectacular telescope ever conceived by humanity is something called the Terrestrial Planet Finder. It will be an enormous telescope in space, frankly probably costing several $1 billion, but what it will do is absolutely unique. It will be the first telescope to take pictures of other Earth-like planets.
To directly view a planet outside our solar system, a whole new telescope technology is being developed.
To construct the Terrestrial Planet Finder that will image Earths against the glare of their host stars, we need some entirely new optical technology, a technology that frankly we haven't invented yet. The frustration is just palpable that we actually know vaguely how to detect other Earths, but we don't know exactly how to build the optics to do so.
NASA envisions the Terrestrial Planet Finder as a suite of two very different but complementary advanced concept telescopes. The first, the Visible Light Coronagraph, consists of a large optical telescope with a mirror at least 100 times more precise than the Hubble Space Telescope.
A coronagraph is a single telescope which collects the light from a star and focuses the light at the back end like a normal telescope. Except at that point, we block the light from the star and we try to let the light from the planet come through. By doing this, you cancel out the scattered light in the instrument, and so you allow yourself to be able to look at this planet which is 10 billion times fainter than the main star.
The second Terrestrial Planet Finder mission will be an interferometer.
An interferometer works by taking the light from a star that comes in and capturing it with two telescopes, sometimes more. And this combined light can be arranged in such a way that the light from the star disappears. That's good in the sense that you now can look at the planet that's next to it, and the light from the planet does not disappear. That's the magic of an interferometer.
To get all this done, new levels of precision in control and command technologies need to be perfected. Something that could take years to develop. The quest for the holy grail of astronomy, another Earth outside our solar system, has pushed scientists to speculate about how such a discovery could affect us.
I think if we find another Earth out there, that's going to have an enormous impact on society. I think to know that we are not alone, that we are one of many potential sites for life, I think will cause a huge paradigm shift in people's thinking.
But there's also the possibility that we may be unique in the universe, and that we may well find Earth-like planets, but no intelligent beings on them.
We have to remember something a little sobering. It is still possible that we humans are some fluke on the evolutionary tree, a twig, if you will, that happened on the East African savanna 2 million years ago, and those hominids somehow occupied a very rare niche that hadn't happened in 4.5 billion years on the Earth. It could still be that we humans are an extraordinary rarity in the Milky Way galaxy. In fact, it could be our destiny as a species to explore the Milky Way galaxy and be the first such explorer species. In which case, our destiny would be to find our roots, chemically and biologically, among the stars.
We have a TV picture